In this case, they kind of noticed a quirk of reasoning models like DeepSeek R1, which is that all other things being equal, the longer that they think for a given problem, the more likely it is that they're going to get the answer wrong, which is kind of counterintuitive in some ways. But it's intuitive another way, which is think about like a student on an exam. If it's the same set of exam questions and one student's taking 3 hours on the first question and one student wrapped up in 20 minutes, probably the person who wrapped up in 20 minutes is going to have a better score on the exam.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Jared Quincy Davis. Jared is founder and CEO of Foundry. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Jared, welcome to the podcast.
Yeah, thanks for having me, Sam. Really great to be here.
I'm looking forward to digging into our conversation. We're going to be talking about compound AI architectures, a theme you've been working on for a while, and how they may transform agentic AI. To get us going, I'd love to have you share a little bit about your background.
Yeah, really awesome. Thanks for having me on the podcast, Sam. Yeah, so my background is I'm the CEO of a company called Foundry, ML Foundry. Foundry is basically essentially a new cloud built from scratch for ML workloads. And I think we've been trying to increase the amount of AI progress in the world. We've been trying to make it slightly easier for a broader spectrum of companies to do the types of things that currently only OpenAI and DeepMind can do. And we've been approaching that primarily from an infra perspective. But then also, we're pretty big believers in AI systems co-design, and we've been thinking a lot about what type of infrastructure we'll need in the future for what we think kind of the future of models and architectures will be. And so we've been talking about this theme of compound AI systems, trying to push this and promulgate this in the world. I'm trying to help people understand why we think it's an important direction to kind of push the broader frontier. And so I'm excited to talk through all of this. Prior to starting Foundry and doing this work, my background is as an AI researcher primarily. I was at DeepMind on the core deep learning team, kind of thinking a lot about how to scale deep learning approaches, how to make sure they converge at scale, both the systems and algorithmic sides of that. And also did my PhD work at Stanford with Matej Zaharia and Yuri Leskovich, kind of also at the intersection of systems and kind of ML theory and ML. And so these are threads that we've been playing on for quite a while, myself and a lot of members of our team. And so it's exciting to, I think it's pretty fun time to be alive, exciting to see all kind of the progress.
There's definitely a lot going on.
Yeah, a lot going on. Things have never been more interesting. So it's a great time to be alive.
Awesome. So let's start from the beginning. Compound AI systems. When you say that, what exactly do you mean?
Yeah, great question. Yeah, I think that maybe it's best to try to illustrate this through an example. To talk about why this is an interesting thing. And one of the examples I find most intuitive is actually a method that one of my collaborators, Alex Demakis, came up with. And he calls it laconic decoding. It's kind of really nice. So in this case, they kind of noticed a quirk of reasoning models like DeepSeek R1, which is that all other things being equal, the longer that they think for a given problem, the more likely it is that they're going to get the answer wrong, which is kind of counterintuitive.
That's a bit
in some ways.
counterintuitive.
Yeah, but it's intuitive another way, which is think about like a student on an exam. If it's the same set of exam questions and one student's taking 3 hours on the first question and one student wrapped up in 20 minutes, probably the person who wrapped up in 20 minutes is going to, have a better score on the exam. There's something kind of like that with DeepSeek where maybe it goes down the wrong branch in like a beam search and has to backtrack and, et cetera. And so one very simple method that Alex came up with to leverage this fact in this observation was to basically create 10 replicas of the reasoning model, 5 to 10 replicas, and then just return the response from the first replica to complete thinking. Super simple, kind of intuitive. And so the amazing thing about this is it actually can push the entire Pareto frontier. So it can be faster because you're making 10 parallel calls, 10 replicas, and returning the fastest one. So it's faster on average than just a single call, as long as you can scale out. It's also higher accuracy, given the point that we just mentioned, on average. But then also, very surprisingly, it can actually be potentially even cheaper on average, which is like, wait, how would that be if you're spinning up 10 replicas? How could it be cheaper? Well, as we know, output tokens are typically more expensive than input tokens for reasons we can, double click on. And also, depending on how, long these thinking traces can be when the model gets stuck or on average, in the distribution of kind of tokens, if you basically do early stopping over these 10 replicas, you actually might produce fewer total output tokens, and actually end up saving cost. And so you just push the entire proto frontier with a super simple method. You made 10 calls and had a policy of early stopping on top and kind of the super simple selection function. And that can push the entire proto frontier. You didn't have to train a new model. You didn't spend $1 billion. It didn't take 3 months. That's kind of inspiring. And
To what degree are we talking about in terms of reduced cost, efficiency, and greater accuracy?
so this is a really important point. So on the cost point, it's relatively simple to understand. We've seen gains of over 1000x, which sounds kind of absurd, but you can have the same performance at a much, much lower cost. And to explain that, it's actually pretty intuitive. The dispersion between the most expensive and the cheapest models is quite large. And so, if you can combine calls to the cheapest model, and actually get the performance of, the kind of frontier system, um, you know, that actually it kind of makes some intuitive sense. It's kind of a routing. It's kind of an extension of the concept of model routing.
But you've introduced a new element there, which is changing to a simpler model as opposed to, um, equal models, compare equals models. So, but if we're comparing equal models before we get to the opportunity to use simpler models, what kind of impact are you seeing with that method?
Oh yeah, we've seen really dramatic impact. So maybe just as one headline result, with this work in this paper called Networks of Networks, and we looked at the extent to which you can just compose architectures out of calls to a frontier model and push the frontier, push the reliability or quality frontier. And we found that on tasks that were highly verifiable, you could push the frontier quite dramatically. We saw kind of 9% plus gains on these really, really hard, sticky benchmarks, where typically changes across generations of models were only like 1%. So pretty dramatic leaps. And we also derived this kind of pretty simple equation, this pretty simple formulation that allows you to understand to what extent could you push that in the limit. And we kind of proved that and showed, if you're willing to spend a lot of capital, make many parallel calls under some then you can actually push the frontier almost arbitrarily far on tasks that are highly verifiable. And that's something that we're seeing for example, in the RL reasoning regime. But this is kind of another angle, another dimension to that.
And by highly verifiable, would an example of that be like code generation?
Code generation, math, these things where the model's taste, is better than its execution, or where it's easier to, check an answer than it is to generate an answer. Kind of like, proofs being the canonical example of that.
It is also counterintuitive that you can push this idea arbitrarily far. Like, I would think that there would be like a diminishing returns, right?
Yeah, there definitely are, definitely plateaus at some point, depending on, you know, depending on like the fidelity of your verifier, for example, right? Depending on the fidelity of your verifier, also depending on, it's kind of like in the, also depending on the kind of distribution or variegation of responses that your generators, so if your generators, if there's mode collapse, if you're using the same model, or if there's not a great for diversity in the outputs of your generator models, then this can only go so far. But it's kind of like that, that thought experiment with the monkey at the typewriter writing a book. If you can kind of, you can brute force anything, if you arbitrarily far, right? If you're, if you have a good enough selector, you can brute force it. But yeah, that's obviously not practical, and so that's where some of the interesting things come in, which is from a basic research perspective, what types of methods are more efficient, you know, uh, yeah, in from terms of the cost or the time it takes to converge or to reach those theoretical limitations, those theoretical, you know, I think I'd say limits of what you can do. Like, how can you reach that faster? How can you kind of rein that in? Those types of things start to get really, really interesting as questions. Like the efficiency of these inference time scaling architecture schemes.
We started off talking about, um, taking a single model, parallelizing it, applying early stopping, that kind of thing. I think the implication is like that's like a very rudimentary starting place for thinking about composability and networks of networks. Like, talk about how you evolve this idea and what that lets you do.
Yeah, yeah. So just go back to that example. That example is obviously it's a heuristic. It's kind of a relatively simple method. It may be brittle, but I think it starts to give some intuition for, oh wow, there is this space, this kind of meta space, of networks, and you can think about what types of strategies are more or less efficient. How can you push the frontier? it starts to, I think, give people a bit of a picture of what you can do. But to your point, there's this much broader space. I think that maybe I'll step back a little bit and try to, give people some of the intuition for why we thought infrastructure scaling research would be fascinating in the first place. And to understand, like, you know, what are some of the elements that make this potentially rich? So let me maybe step back and first start with a couple of points of context. The first is that the cost of inference has been falling precipitously for several years. And it's clear that will continue. The costs have been going down roughly 10x per year for the last 3 years, 1,000x, to achieve some kind of baseline level of performance, kind of like, say, GPT-4 level performance on something like MML. It's really, really dramatic. Um, and so now it's starting to, I think, if you kind of extrapolate that trend, which I actually think this is one of the trends that's easier to extrapolate in AI. Like, I think we extrapolate other trends that are sometimes a little bit
To
more
our
perilous to
peril.
extrapolate. Yeah, I think this one's actually slightly easier to extrapolate for a whole host of reasons. But if you extrapolate that trend, then you can start to potentially in the distance envisage us creating architectures where when we say 8B, it's no longer the number of parameters, it's the number of inference calls in some kind of inference system. And that starts to get a little bit interesting. And the question is, by what types of principles should we think about that architecture space? Right? I think starts to be a really interesting, starts to elicit an interesting set of questions, interesting raft of questions. And so that's part one. I think part two is that the ecosystem, in addition to this cost piece, the ecosystem is a lot broader than it used to be. In a couple of years ago, there's really only GPT 3.5 and GPT-4 as options. Now, even just within OpenAI, there's this whole model selector, issue people joke about. There's so many different models, you know, you know. But then also there's other providers. Gemini has multiple generations of models, and then in each generation releases a family of models now, going from Pro to Flash Lite, and they actually, you know, Claude, I think, somewhat started this with Sonnet, Haiku, and Opus in Claude 3 generation, right? Kind of invoking implicitly or explicitly this notion of a Pareto frontier. Gemini is now very explicit about that notion of Pareto frontier and actually says that they define the frontier, that, whether you want high quality and reliability or whether you want low latency and low cost, you know, a Gemini model will give you the best, right? And so I think we've seen that. We also have obviously open source model providers, Meta with Llama, DeepSeek, it's Grok and XAI. It's a lot more diverse than it was, and I think arguably in some ways more diverse than people expected. At least in some of the people around me expected. And so,
I mean, especially considering the um, early observation and conversation around how expensive it was to train these models, there was a period of time where we thought that there would be, only, three model providers in the world because it was just such a Herculean effort to train these. And now we've got this Cambrian explosion of models for, every need.
yeah, that's right. Yeah, I think that's been really interesting to watch, and I think as a result, across both providers, but then also across models within a single provider family, we've seen this massive dispersion emerge where the difference in cost between the most expensive model or system, should I say, and the you know cheapest system is quite wide. There's a massive gulf. And so O1 Pro was, maybe they've changed it, but O1 Pro was $150 per million tokens, whereas DeepSeek R1, was 3 cents per million tokens. That's quite a dispersion, right? And so you can make a lot of DeepSeek R1 calls for one O1 Pro call, right? And so it kind of starts to get your mind wandering, what could we do? Obviously, routing is a basic idea. You'd say, okay, if it's an easy question, then cheap models are already saturating that level of intelligence, so I'll just send it there. And that's something that one of my collaborators, Ling Zhao, did early work on, stretching back to 2023, 2022. That was really fruitful. And is a bit of a richer problem than one might think on first blush. But then also you can start to say, beyond just routing among these monolithic models, to what extent can I combine models? You know, can I combine calls to R1 Pro? Or can I even do kind of funky things where maybe I have O1 Pro, where maybe I can do rich things where I send something to R1 initially, get it to somehow reframe the question. So I'll use fewer tokens from O1 Pro, something like that, right? And so you can start to envisage doing all kinds of, funky things. And, basic research comes back into play. Things get exciting again. It's not just, the most blasé form of scaling things up. Yeah, things start to get rich from a research perspective. Academics can contribute. It becomes a really dynamic ecosystem again.
Yeah, and you can even imagine like forgetting the term for it, but you can imagine like generative networks of LLM networks, right? Where these are created on the fly, or they're created, if not on the fly, kind of in a batch mode, and then explored for their efficiency. Uh,
Yeah, exactly. Yeah, exactly. And yeah, you couldn't say better. So, there's these are some of the kind of first principles reasons why it's like, this is interesting. And at the same time, as all this dispersion's emerging in terms of cost, we're also finding, hey, things like distillation work extremely well. We've known this for quite a while, but I think people are starting to appreciate better and better just how much you can, if you have a specific task that you care about in mind, just how much you can reduce the cost, and preserve quality and reliability. Just how dramatically you can push that, so how extreme it can be. So we're seeing that, and there's also one more point which I'll invoke, which is a bit more up in the air still, but I think it also seems to me like even at the frontier, the things are very jagged, number one. And number two, the affinities of respective providers and models are starting to become clear that these different systems have their own affinities. Claude seems to be going more in the sense that, Claude seems to be going more and more after agentic coding and practical coding, like there are choices being made in data set mix and the objective function construction, in the way that the evals are set up that seem to be saying this provider is going to focus more on this set of tasks, get better at it,
Certainly on a model by model case, if not by provider. Like, the coding models, writing models. There are companies out there trying to do domain specific models of, for a variety of use cases.
Yeah, you see it in languages as well. The QN models from Alibaba are better at, Chinese, idiomatic Chinese, things like that. And you're kind of seeing, these, the fact that these models have different affinities emerging. And right now, it might seem like the differences are relatively narrow between models, and they're all kind of at the frontier, and the jagged peaks are kind of, aren't that deep, or, are relatively shallow. They're not that high, rather. But I think when you project into like a more agentic world, compound systems compound errors, right? And so these small differences accumulate. If you have many, many steps or long horizon tasks, these kind of small differences that becoming big differences. It's like that, that's kind of funny example, 1% difference per day over a year, that type of thing. You start to see, big, 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 big gulfs emerge.
Although that, to some degree, that implies like a uniformity of performance per model per use case. And I'm not sure that we necessarily see that. Claude may be on the broad average perceived as better for code, but for a lot of specific things that a given user is trying to do, maybe Gemini's better, maybe O1's better. And so I would think that a challenge that one might want to address is finding ways to use these compositional networks of LLMs to get better average performance on all tasks as opposed to like do really well on some benchmark task or something like that.
That's exactly right. And I think the fact that, to your point, even within some broader kind of regime or some broader task family like practical coding, which is hard to define, there might be one model may be better on average, but then there might be big gulfs if you further, stratify that. I think that's important. And that's actually why this is such a rich thing. If it was just this model's better at coding, this model's better, then that'd be a relatively simple graph that you'd build, a relatively simple router graph. If it's at the level of a individual question, if users' own preferences come into play, things start to get a bit richer. Um, I think that one kind of piece of work that we did that kind of, I think, illustrates this really well is this work that my colleagues named Ling Zhao led called LLM Selector, which basically was asking the question of if you have a multi-step pipeline task, some tasks with multiple steps. Let's say you have a bunch of different models you can choose from. Will you do better by, mixing these models to do different parts of that pipeline? Or by taking the best model, the model that did the best monolithic model that did the best on all steps of the pipeline? Meaning if I only have, let's say GPT-4, or let's say O3 now, for a given task, versus if I can Mix, O3, and Gemini, etc. Will the only O4, only Gemini 2.5, only Claude 4 system do better? Or will the kind of hybrid system do better than the best system among those? And it turns out that the hybrid system does better.
What's an example of the type of multi-step task that we're talking about?
Yeah. So there's a whole set that we chose partly to, you know, to show this is a general thing, not task specific, but a lot of the most kind of exciting tasks that I think everyone's still trying to work on are like the coding, kind of agentic coding tasks, like those types of benchmarks like SweBench and things like that, where, these are, I think everyone's really excited about these types of tasks at the moment. But there's a few others in kind of math and chat. There's a few others, like kind of somewhat artificially constructed ones as well to illustrate this. But I think that the kind of like SweBench, types of tasks are the ones that are extremely practical, extremely useful, and really exciting.
Yeah, so that raises another issue, which is it's not even the task that we're specifically talking about, it's the approach to the task. So you talked about a multi-step. Uh, what I interpreted you saying was using different models for each step of a multi-step approach to solving a task. Like Sweetbench, you can solve those one shot, or you can like break them up into more of an agentic flow and solve them at a variety of different granularities. And so I was trying to get a sense for like what kind of granularity are we talking about here?
I think one of the points that I'd highlight is that when you start to think about these compound systems, there's multiple ways you can optimize them. And that's why I think it's starting to spawn a lot of new research. It's starting to kind of engage the academic community again, where they felt left out previously. You can optimize prompts over fixed models in a fixed structure, kind of DS Pi style, which our collaborators, Omar and Matei, did some great work on, right? Which is very popular. You can optimize the weights of a verifier or router. You can optimize model selection. You can optimize the architecture of the non, right? We've been talking about, that laconic decoding example where it's kind of an ensemble in some sense, right? You can optimize that, the width of it, the structure of it, etc. The type of function that is your aggregation function or your selection function, etc.
And when you said non, you're saying network of network.
Network of network. Yeah, exactly. I'm trying to make this a thing, I suppose. It's like, so I'm just assuming, just acting like it's a term everyone knows. Exactly. Network of network. Right? You can also, change the hyperparameters of the model calls. You can say, I'm going to change the temperature. Like maybe it's the same ensemble of GPT-4, but I'm changing, the generator temperature to elicit greater diversity among their responses that I can then use, right? To further explore space. So you can also do distillation if there's one part of the system that is linked to a lot of cost. You can fine tune or distill, right? So long story short, there's many dimensions. They all have their own cost, infrastructure, time, etc. implications. And it's rich to think about how would I search this? What's the most effective way to navigate this space? Optimizing prompts can get pretty expensive pretty quickly, even for shallow pipelines. You know, if you try to do that over some large network of calls, that might be really difficult, depending on your approach and how you're searching. Right. So this starts to get really, really cool. This starts to be a really neat area. And, there's a lot of room to gain given that dispersion we talked about, given that the cost between the cheapest models and the largest models is so vast, given that these models can give you an answer that is one output token if you frame the question correctly, or it can give you, a million tokens of output, if you frame it wrong. Um, all these things contribute to saying, okay, there's a rich space here. And I think it's starting to come into view. People can see it now a little bit. And, basic research has a place again in a new way, and you can kind of do experiments at small scale, develop an intuition. Because some of these approaches, they just are small scale, like your best of n graphs or your ensemble graphs don't have to be massive to push the Pareto frontier or to push the frontier. So that's kind of this domain. I have a pretty biased way of looking. I think the term compound systems is a little bit nebulous still, and there's a few ideas that are kind of being jumbled into this banner. Um, I think that another idea that comes up a lot is kind of tool use, which we haven't talked about. We've been primarily talking about this kind of inference-time scaling architecture approach to it, but there is also tool use, and we can double click on that a little bit as well. But yeah, I think that gives you some family, some intuition for this family of questions that we have been really inspired by. And
Before we dive into tool use, in the LLM Selector paper, you mentioned that they identified that this hybrid system can outperform a monolithic system. Did they also provide any guidance for folks that wanted to go down this path, like how to optimize the use of different models in a given system?
Yeah, yeah. LLM Selector actually is now a framework that has, some algorithms in there that can kind of automatically help optimize this. That's right. They can search the space. It's still relatively in code research, and so I think there's a lot of work to do to push the efficiency of this, to et cetera. But yeah, there's actually a code base associated with the paper that you can find that can start using, and a number of people have been doing research extending it. Yeah, so I think this is going to be a really rich area, and it's already becoming rich. Yeah, maybe just to make another point here, I'll just note, and this is a broader branch maybe we should go down, maybe a point around, you know, co-design, kind of systems and algorithm co-design, um, to give a little bit of intuition for why it starts to get interesting and why, from my perspective, at the cloud and scheduling level, this is really fascinating. Imagine two very different systems. One system is, kind of a vertical inference time scaling. You know, like you're basically producing longer and longer chains of thought to improve reasoning capabilities or to, kind of push performance and use more compute at inference time, invoke more compute at inference time to, push quality. And that requires more and more HBM. Probably what you want in that case is a kind of scaled up system. You want high bandwidth memory, exactly. You want more and more GPU memory so you can keep all of that in context. You want a bigger system that's connected via NVLink. Maybe you want an NVL72, like NVIDIA's newest system, kind of the big box, right? There's another case, which is kind of more that alpha code to kind of more classical thing, which was maybe one of the other ways that you can invoke more computed inference time is horizontal inference time scaling. Maybe I want to instead say I'm going to spin up a million replicas. This is literally what they did. A million replicas, and I'm going to ask each coding question, each replica, right? And I'm going to 1,000,000 candidate responses. I'm then going to have some protocol for filtering these 1,000,000 candidate responses down to the best one, or to the best, in the case of AlphaCode 2, best 10 that I can then try one by one, and see if the test pass. But you have some kind of best of n construction. These are very different. In the best of n case, I might want 1,000,000 GPUs for 400 milliseconds to do these inference calls. I don't care if they're interconnected. They can be part of different InfiniBand domains. I don't really care. In the vertically scale case, I want a highly interconnected system for 10 contiguous minutes. And everything should be part of the same domain. It's one contiguous block of compute. These are very different cases. They also might have different implications depending on the task for the performance I can expect. But these are very different cases from a systems perspective, right? And so one of the things that's cool for us is saying, okay, to what extent, like, these things should probably be priced differently. They should be scheduled differently. If there's too much of one, then the other then becomes actually a little bit better. It's like, hey, there's a lot of contiguous compute blocks already allocated that I can't disrupt. I can fit, kind of less contiguity requiring workloads in between, et cetera. So you can kind of push, nudge, you can kind of nudge things. You can kind of nudge to use this broader pool of resources really efficiently and say, hey, I've got a lot of stranded workloads because I've got a lot of contiguous work going on, a lot of contiguous systems. So I've got a lot of stranded stuff. So if you have a stranded workload, be my guest. Come fill this. Actually the costs are going to be relatively low because it would otherwise be stranded and unutilized. And then vice versa. So it gets really, really neat. And so part of the thing that we're trying to do with Foundry, but also with this research on compound systems with our broader set of collaborators, is trying to, make sure that as we get into this world that's highly agentic with this diverse, almost ecosystem of systems occupying their own ecological niches, that we have the infrastructure that can actually support this, that can, in the right way, in an elegant way. So hopefully that makes some sense.
No, it does. It calls to mind for me the world of, call it like this transition over a prior era from supercomputing to distributed systems, right? There was a time in which, in order to run any large computationally intensive workload, you needed computer systems with shared memory. And then eventually we got to things like Beowulf clusters that had some degree of shared infrastructure. And then over time, more and more of those workloads that required this like highly integrated system got chipped away. And now, you've got people running a lot of the things that used to require these supercomputing systems on Kubernetes clusters and highly distributed independent systems. And a lot of that was changes in algorithm. A lot of that was the development of tooling. And just hearing you talk about this, you can kind of see the same thing playing out on the AI side, where um, because of the lack of the infrastructure work or the algorithmic work and the frameworks for some workloads, you might just want like NVIDIA's biggest box, but more and more of that's going to be using inference parallel or parallelized types of invocations in a very distributed setting.
100%. Yeah, that's a really good thing you're raising here. Yeah, I think maybe two ideas. One would be I think there's a pendulum, right? And it's almost like a competition. You know, there's almost like a deeper way to explain this. But essentially, I think there's a lot of things that people talk about, which is, hey, will more of the work be inference or will more of it be training? And I find a lot of these questions, you know, I don't think they're the right questions. For example, I think that these things will always balance each other out. So, for example, I think one of the things that we all know is if you're doing a lot of inference, then you might actually want to train your model so that they're cheaper to inference, meaning distill them, meaning overtrain a small model, kind of pushing the chinchilla scaling law somewhere they shouldn't go or they weren't initially intended to go. So you have, overtrain a small model so it'll be cheap to inference and the lifetime costs are lower, etc. So there's kind of a natural way in which these things will balance out. Yeah. Yeah. And so I think that what this kind of hints at is that point I've been kind of hammering, which is around co-design. I don't think that people fully appreciate the extent to which the systems that we have dictated the types of research you know, that's been ascendant over the history of deep learning. Frankly, I think deep learning overall, part of the reasons deep learning is the ascendant ML theoretic paradigm is because it scales so well. It's kind of a bitter lesson type notion. It scales so well, it assimilates compute so effectively. And so as Moore's law progressed, deep learning is one of the methods that could take advantage of that. Same thing with the methods within deep learning that have been really ascendant. Just a super dense transformer attention computation versus kind of a neater LSTM type of thing that's not as efficient at, using the fact that we have these really, really dense parallel systems that are, initially designed for graphics in some sense, but are really, really good at, these kind of dense matrix operations, etc. Like, I think that the people don't fully appreciate this. And so, you know, one of the things that I guess is exciting to me about, the next little while is I think we are going to see, to the extent that people all converge on one approach, vertical inference time scaling, whatever it may be, I think we're going to see that actually opens up, kind of creates, as long as there's a system that can actually manifest this, like what we're doing with the scheduling, if there's a lot of contiguous blocks of work, that actually frees up a lot of gaps. And if any type of workload that can fill those gaps, kind of is occupying an ecological niche to itself, right? And isn't facing competition in the same way. And, that can be cheaper. And so I think that these things will balance out and the pendulum will continue to swing as it has for quite a long time. I think you invoke kind of the MapReduce and the history of these things. And I think that's very much going to play out. I think we see the same thing with async kind of work versus real-time work. I think you'll see that as methods are more and more real-time, there'll be a computational benefit to having things that can run in batch mode async in the background. And, I think these things they'll be very, 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 very diverse and interesting landscape going forward. And so I think if you're a systems and ML person, there's never been a better time to be alive. And I think for people who are on one side or the other, I'd encourage them to, try to get more familiar with the other side of that.
Yeah. So, and kind of thinking about all that we've discussed with regard to compound AI systems, like practically speaking, if you are, machine learning engineer or researcher and you're trying to actually do something, like how do you take these ideas and put them into practice?
Yeah, for sure. I think that for now, the one primitive or the one idea I'd encourage people to think of is just ensembles or best of n. As a reduction, as the community gets more and more intelligent. I think that in the case where you want to push the reliability or quality frontier, which I think that's where most people are. I think most people aren't trying to optimize costs yet. In my biased view, they're not yet at that stage. They're trying to get it to work. They're trying to, they're trying to get to work, trying to make the reliability good. They're also trying to cross that demo to real time chasm where you start being judged not by the outlier good examples, but by the outlier bad examples, right? They're trying to make sure that everything works. In that case, they want GPT-6 early. They want GPT-7 early. I think one of the really simple ideas that people can try to employ is just calling the frontier models multiple times and trying to combine the answer, at least on those verifiable tasks. That's a really simple thing that works pretty well. And actually, in this network of networks paper, we're able to characterize when this will work well and by how much it will help in terms of three simple numbers. The numbers being some base difficulty or just a base likelihood that you get the answer correct with one call. And then also some, basically soundness and completeness number, which is a characteristic of a verifier, which is if an answer is right, how often is a verifier model able to certify it as right? And in a case where an answer is wrong, what's the fidelity of the verifier in terms of saying, hey, this is wrong and rejecting it? If you have those three numbers, a base correctness probability, a verifier soundness or certification probability for correct answers, and a verifier rejection probability, then a very simple ensemble or best of n structure with generators and a judge will push the frontier pretty reliably. Obviously, it will increase your costs as well, but these models are actually overall pretty cost effective, at least at tasks that aren't many step or multitask. And so I think that's the thing I would encourage people to try. And we actually have this framework called Ember that we created, trying to make these primitives really, really simple to construct and express and efficient to run. We're trying to make this easier and easier for people to construct these things. And I think that base ensemble, is already a great place to start and also has other nice benefits. Like you can use the disagreement between ensemble members to get some sense of, okay, is this thing hallucinating or not? You can I think that's already a pretty good place to start, to try to employ these ideas in their own work, to get things that maybe weren't working to work. Yeah, so that's what I'd encourage, and but also I'd encourage people to follow this area of research to start being creative themselves. I think we're in the early era. It's kind of like 2010 deep learning, where a million flowers were blooming and there were live ideas and stuff was just starting to work and people were really excited. I feel like it's 2012 again, but in this in this new kind of networks of network setting, not neural networks. And so I encourage people to say, hey, it's 2010 again. That was a fun time. The 2010s. Like, yeah, get excited. Do research. If you're an academic, you can push the frontier now. You don't need to be at a frontier lab. I think that's what I encourage people to think about.
With regards to Ember, what is describe that as a framework to work with? What are the ergonomics of it, the developer experience?
It kind of came out of our own research on these architectures, on these inference-time scaling architectures, and we wanted to kind of be like what Torch was for neural networks for networks of networks. So we want to be fast to run, fast to write. The contributors, a few of them were the original contributors behind Ray and Spark, and so Ember is from that same family. And so we're reusing that Spark banner of fast to run, fast to write. And so it should be things that would take a long time or be have all kinds of little pitfalls like constructing these big graphs, these big almost like neural network graphs, but out of inference calls. Want to make that really simple, concise, and then also want to be efficient in the sense where just like with neural networks, there's vectorization, you know, some parallelization, etc. You can do that here, where maybe if you have a large graph of calls, you want to do some type of topological sort and parallel dispatch rather than just doing a for loop, right? And so it'll run faster, and you won't be super slow. So we want it to be concise and also pretty efficient in terms to run these things. And so that's what it is. It just has a little bit of like a Jack/PyTorch ergonomics, but then there's also like a kind of Unixy string-based compact syntax that someone built as well. But primarily it's kind of like Jax or PyTorch, but instead of neural network modules and nn.linear and nn.dropout, things like that, it's these network-to-network modules and non.ensemble, non.judge, things like that. So it's just a bunch of primitives, tested, validated, kind of make it easier for people to do this work. And we've been using it with collaborators spanning a pretty broad range of you know, universities and also companies. And we've been, there's a lot of really cool work going on that I think will be coming out over the coming weeks and months from the community. Some projects I'm pretty energized by that I don't want to steal their thunder by leaking any results. But yeah, I think that's the goal of that, is to make it really easy to search this space, just like Torch made it really easy to search that neural network space in the 2010s.
And kind of looking through the code on GitHub, or sample code on GitHub, the basic ensemble seems fairly straightforward. I think where some of the complexity might come in terms of how do I apply this to my use cases, rather in like the voting and the judge elements. Can you talk a little bit about how one should think about um, building those out?
Yeah, I think the most basic variant is already works pretty well. So I would encourage people not to overthink it for the first variant. The most basic thing is just these models are already pretty smart, and so you don't have to have a really fancy prompt, to start to get some advantages. You can just have a number of generators. Let's just say as a default. I think the default in the system is like 10, um, 9 or 10. I think it's actually typically an odd number depending on the aggregation function. And then you have a judge, and the judge is some bigger, more powerful model. The generators can be that same model or some cheaper model, and basically just ask the question to all of the generators, tell them to generate candidate answers, and then you just feed those candidate answers to the judge and say, "Hey, here's some advice from your advisors. You know, your council of advisors. You list it. Given all of this, you know, produce a final response to this original question and give the question." And that very simple construction is often pretty helpful. People can test it a couple times in their setting, and see if it helps. But it's often quite helpful.
Yeah, I'm thinking about this in the context of a use case that I've worked on, which is, surprise, surprise, podcast transcription, right? And what I've found was that, like, particularly for a technical, podcast like this, there are a lot of names and places and things like that your off the shelf transcribers would get wrong, and so the approach that I ended up taking that worked really well was to you know, scrape a lot of information about a guest, like the stuff that they've worked on online, and then uh, like essentially paragraph by paragraph and ask a model to, given all this information we have, like what in here is probably a transcription error and not right. And it works really well. But in light of this conversation, I'm thinking that another approach would be just do it 10 times and, have something like try to rationalize across those 10 times, because it was often the case that, um, it's just a randomization, the random nature or probabilistic nature of this, where sometimes it would be right and sometimes it would be wrong. And the additional machinery that I built, like it increased the likelihood that it was right, but it wasn't because I was necessarily introducing new information. It was just like biasing it towards that new information, if that makes sense.
I know exactly what you mean. Yeah, 100%. Yeah, two ideas come strongly to mind here. One is in this R more LM calls all you need paper. We're able to kind of characterize what you're describing a little bit, but also find out when this doesn't work, when it does work. And it's actually very nice intuition. Basically, there's what we change between the networks of networks paper and the R more LM calls all you need paper is the nature of the aggregation function, right? So they're both ensembles, but in one case, you're doing best of n. In the other case, you're doing most common of n. And these have very interesting theoretical properties. Most common of n, it's like, democracy, right? It has some, it
It's
works
like a
really, really well.
quorum type of
It's
approach.
quorum. Exactly. We found that simple idea does work really well, but only in cases where it's an easy question. And the default model would have gotten the answer right, but there's some probability that it hallucinates. In that case, the variance reduction of the ensemble quashes that hallucination probability. And so you kind of converge on 100% accuracy.
And my intuition is that that probably is not the best approach in my case, because, oftentimes it's like some obscure acronym or something that it's it would get probably 20% of the time right, but not 80% of the time right.
Exactly right. And so in the other case where it's a hard question, the variance reduction actually hurts you, right? It removes the outlier probability that you get the answer right. And there's actually some funny organizational design implications, like, for, breakout ideas, you probably don't want consensus or,
Mm.
decision by consensus or committee, you know, but I'm
Right.
extrapolating a little bit, but, I think it's kind of fun to think about. That's a property of this type of voting-based or quorum-based system, or your consensus-based system rather. In the other case, with the best of n, you don't necessarily see this, right? It has its own properties, and it's actually more monotonic, in terms of the more ensemble members you have, the more calls you have, the more that kind of leads to a performance increase, regardless of whether you're in the hard regime or the easy regime, which we can talk about. It has to do with that verification versus generation complexity asymmetry notion and the soundness completeness notions, which are characterized in that paper. But it's kind of funny that number one, there are differences in this, you know, the behaviors of these different types of systems, and then also you can think about how that applies to your case, right? I think it's a fun set of things. But yeah, I think in your case, that's a really neat example. This kind of you know, trying to the transcription error resolution thing. Yeah, that's neat.
Yeah, one thing that occurs to me in this context is, say we're going for, best of n, and do we end up with a case where now my, single judge is a single point of failure? Like that thing hallucinates and it destroys my whole, it doesn't matter how many generators I have because I'm really dependent on the judge.
Yeah, that's totally right. I think that so there's a couple ways that you can do this. So the construction we study in the networks of networks paper is actually a specific type of judge, right? And so this actually is a funny question. Like, what should the judge's prompt be? How should the judge work? The construction that we study for theoretical reasons is what we call a verifier-based judge.
It implies, though, that your problem can be verified, like it's a verifiable task.
It does, but actually, even if it can't be verified, it's an interesting construction. So the way it works is, let's say you have 10 candidate responses. You can show them one by one to a judge, and the judge is just trying to produce, is this correct or is this incorrect? Thumbs up, thumbs down. That's all the judge can do. You know, that's all the judge can do. And so now that starts to get interesting because, and then if the judge says everything's wrong, then you return a random answer, or you return the first thing that the judge says, yeah, this looks good. Now, the funny thing about that really simple protocol is that it doesn't necessarily make things worse versus like your average case of the, initial of like the generator likelihood. Like unless your judge is like more likely to certify a wrong answer as correct than a correct answer as correct, which is kind of extreme. So, but you can look at those properties. It's kind of funny. I kind of like this because I like cryptography a lot. I like theoretical computer science a lot. It's kind of funny that like those kind of P versus NP ideas, of like how easy it is to verify something versus certify those cryptography ideas from like probabilistically checkable proofs and PCPs come in here, where very rarely is that going to be the case. That like you'll have some model that's so ill conditioned that it's like more likely to certify a wrong answer is right than a right answer is right. But that's something you can study probabilistically and empirically, on some subset of questions, a holdout, etc., and kind of try to get a sense of that, right? But as long as that's not like really skewed in a bad way, then you're actually pretty likely to, you know, like see a gain from this. With high probability, see a gain from this verifier-based judge construction, right? And so, I think that kind of highlights that there is this design space. A normal judge might be bad, like, might be overwhelmed by context, in some way. Like there might be issues that or it might just be more expensive. This verifier-based construction can be, you know, it's kind of funny. Like the properties of it they are really kind of clean theoretically, in a way that you can kind of guarantee and be confident about.
Does this verifier-based judge and limiting it only to kind of thumbs up, thumb down mean that you could use much cheaper models for verification, or is there still a requirement that you use kind of a more powerful model as your judge?
Yeah, you can definitely use much cheaper models, for verification as long as, that kind of soundness, and completeness story is correct, and That's right. And so it doesn't have to be a powerful model. That's 100% right. It's kind of a function of the, likelihood that you certify a correct answer versus the likelihood that you certify an incorrect answer type of thing, right? So you're right. But then also another nice benefit is the thumbs up, thumbs down also is nice because, you know, input tokens are way cheaper than output tokens, and so there's kind of something nice about if the output is
Kind of a
just
token compression in your judge layer.
exactly. If the output's just thumbs up, thumbs down, that's actually pretty, and then you're just returning the answer that was already generated by generators, that kind of, plays some role into this kind of cost equation as well, which is kind of fun, which is kind of interesting to start to think about.
But you didn't talk about kind of parallelizing that judge layer. Like I was envisioning, you can, turtles all the way down, like, highly distributed networks of networks of networks with each layer being very parallel. Is that something you've looked at?
100%. Yeah, exactly right. So, to your exact point, you could say maybe the judge itself should be a network, right? Or maybe this whole little primitive of an ensemble plus judge should be a node within another network with a judge. It's kind of trees, right? And so it starts to get pretty rich, and so you start to have deep networks of networks instead of deep neural networks. Denons, etc. And so it starts to get, and you can start to visit, and then you start to think about, oh, there's loss in the middle dynamics, right? We know that these models have somewhat limited context, right? And so you can't feed an infinite context length, or even if you do, quality diminishes. So maybe you do want to break things up and have kind of smaller domains where fewer generators are going to a single judge, and then you're aggregating. It's like representatives, right? This whole architecture layer emerges, or maybe there's some notion of skip connections that starts to emerge where you're like, oh, well, something way down below got quashed by this judge layer, so I need to kind of feed it up, right? You kind of get back to these deep neural network concepts of vanishing and skip connections, and these things come back in cool ways, which I think is really exciting to start to think about.
And it reminds me of the term that I was searching for before, but like neural architecture design is an idea that comes into mind here, like where it's network of network design, where it's a highly automated process that, well, now I'm thinking like, I've seen evolutionary approaches to this and, other approaches of searching the space. It can get pretty interesting, but I don't get the sense that we're quite there yet.
Not quite there yet. Yeah, not quite there yet. It's still the very early days. A lot of the work that's been so far is like those early days and like perceptron research and MLP research. We had like these, like kind of wide but relatively shallow networks, and they had relatively few parameters. And then and over time we scaled them up, and things got richer and richer, and we started to run into vanishing exploding gradients and started to think about ways to combat that, and it kind of started getting richer and richer. I think we're in those very very, very early days still. And partly because I think the infrastructure doesn't support doing richer research. Like, the latency is going to kill you if you try to make, 1,000 calls to GPT-4 with for loops, nested for loops or something. It's going to get pretty ugly pretty quickly, and also it's going to get pretty expensive pretty quickly. Um, but then as this dispersion emerges more and more, as distillation works better and better, as we have cheaper and cheaper systems, and as you have the infrastructure like Ember to make this faster and faster to instantiate and run these types of ideas. I think there'll be more and more research, and over the next months and years, I think it'll start to get wild, where we'll have multi-billion parameter networks of networks, with very kind of intricate structure.
And you kind of alluded to this earlier, but you can almost see a world in which you've got some problem, you kind of define your problem, you have your data, and then you, as opposed to training a model, you evolve a network of networks, and then you distill that network of networks down to a simpler either model or network of networks. And so I'm wondering, like, um, yeah, and I guess we're way, we're even further out ahead. But I'm wondering, do you track any research that looks at like network distillation? Are we anywhere there yet, or is that still to come?
Yeah, I think that we see early forms of this already in some of the reasoning research. Yeah. So actually, I want to make maybe 2 points about ways in which compound systems are already kind of around us, but that we don't really recognize as a compound system and haven't like taken those examples to their limit. One is speculative decoding, and the other is what you just mentioned of kind of distillation of networks, right?
Would you add MOEs to that mix as well?
In some sense, yeah, in some sense, that's definitely true. Although maybe in a slightly different way. Yeah, so let me start with speculative decoding because it's just so common, but, and it's everywhere and et cetera. So speculative decoding, you have kind of a funny little compound system where there's a small drafter model and then a big verifier model. And the idea is you can get greater efficiency. That's kind of like it pushes the Pareto frontier in terms of latency versus quality in a way that's provable that you're not losing quality, but you're definitely getting an expected improvement in latency, in speed and tokens per second throughput. This is, it's kind of obvious. But the way it's doing it is you have the drafter model is running ahead, and then the verifier model is kind of in parallel, rejecting or accepting multiple tokens, right? And this is kind of is a funny case of, at least a very simple hybrid system with a small model and a bigger model being combined to push the frontier, the kind of Pareto frontier for the overall system in terms of cost, latency, etc. And it doesn't actually increase cost by as much as people might expect because of this fact of a GPU, which is kind of funny, which is you want to oversubscribe it, you want to keep it utilized, the cost is mostly CapEx, etc. And so having that smaller model doing things in parallel that then could be verified by the bigger model doesn't actually increase your cost in the way people would maybe imagine, right? And so that's one very simple example of a compound system that's kind of all around us, but we don't think of that way. Another is what you're talking about, which is more this, distilling a network of networks. I think we're kind of already doing this with when we have many, many replicas in kind of a standard RL pipeline. You spin up many, many replicas, you ask them to do questions, they all produce candidate responses. Maybe one of them's correct, and that's the trace, that's the rollout that you end up, you know, you're training on, overweighting in your training, right? That's kind of a funny case of using compound systems, but within the kind of framework of RL in a more classic way. Rather than using that to generate training data to then train a single model, you can imagine that system itself being something you just do at inference time, right? And there's obviously the whole spectrum. And so, and by the way, this type of thing's been done multiple times where in a lot of this chain of thought research, one of the basic things people have been doing is saying, let me go ahead and do multiple steps, multiple step rollouts of the current state of the art model, get it to generate 10, you know, kind of sequential improvements, based on some question, just initial reasoning. And then let me take that entire thinking trace and use that as my training data to train the next generation of the model, to then try to produce that whole 10-step, you know, reasoning trace in one step. And then let me try to bootstrap off of that, do that again and do that again, right? There's, and obviously there's all kinds of trouble in that potentially, this, persnickety thing. But I think you can kind of see, you can kind of see the contours. You can see how that would work and how that would extend that type of thing. So I think that's been already in the works, implicitly at least for a while. Yeah, 100%. And yeah, it's pretty interesting. Yeah, I think something that I don't think, everyone maybe knows or has intuition for is we mentioned earlier how shocking it is that distillation works so well and just how well distillation works. I think even at the hardware side, I don't think people appreciate how well ASICs work, application specific integrated circuits, how well these, when you have a task in mind, if you can design the chip for it end to end, how well this type of things works. And I think that's why the kind of, compound systems or system of models or menagerie of models type of vision, I think the GPU in some sense is a proof point that you know, application specific system built in a co-design way with an end use in mind can really push bend the curve, on cost.
Yeah, it's interesting that like you can, there's one lens in which a GPU is a general purpose uh, building block. But then there's another lens that you can look at it as an application specific building block for graphics and now AI.
Yeah, very much. It very much is, right? And I think it was kind of obvious that the CPU is not the right form factor, for a lot of use cases, in a fundamental way. And that's why you need accelerated computing, and that's why you need the GPU in a fundamental way. I think people haven't taken that to its limit, or even recognize, at least, obviously there's some natural, you wouldn't necessarily need, infinite variation, infinite specialization, but there's at least different poles. And we've seen this in the last few years of deep learning, where the TPU is very much explicitly described as a co-designed system, where there's, elements of, what level of precision do you need? right? The precision format, the kind of design and its in the extent to which it's well suited to parallelism, but then also the models themselves and the actual learning algorithms and how tolerant they are to noise from lower precision, etc. Like all of these things co-design into one system. Yeah, I don't think people have kind of really appreciated this, and so I think when it comes to that question of will the future be compound systems or will it be a single model, you know, I think I basically point people to at least the CPU versus the GPU to say at least there'll be a couple of different polls, right? There'll at least be that kind of perhaps small model, highly distilled, with big models, at least that type of pairing, if not something even richer. Uh, so yeah, it's a. I think that goes back to this kind of theme that I'm continuing to push, which is one, basic research is back and there's a lot of work to do, but number two, kind of it's never been more interesting time to do co-design and to have both the systems and ML or engineering and research perspective on these things.
And bringing this all full circle, like given this viewpoint about the way that ML systems are going to evolve and kind of, scaling out of distributed inference, makes perfect sense that you'd start a company at the compute layer doing inference.
Yeah, for sure. I think the way that I thought about it at least is it was pretty clear to me that compute is really a root node problem for ML. I was very much kind of an algorithms deep learning person. Um, but it's pretty clear that part of the reason that deep learning is the ascendant ML theoretic paradigm in the first place is because the way it assimilates compute. And so in some sense, deep learning is a root node problem for all of these downstream applications across health and education and, materials and all these things that I think are really important and interesting, robotics, yeah, you name it. But then the problems that are kind of upstream of deep learning are largely the systems problems. And it's pretty clear to me that the cloud as we currently know it, the algorithms, the economic model was not well suited to deep learning. And it was really going to narrow our creativity, limit the types of things that we could do. And then it was already hurting companies where they would have to raise tons and tons of money to buy a long-term contract. The cloud just wasn't working the way it was supposed to. The whole promise of the cloud of elasticity on demand, infinite compute on demand, on tap, not needing to capacity plan, that whole notion was not being fulfilled in the AI cloud context. All of the desiderata of the original cloud, none of them were being fulfilled really in the AI cloud context. Almost all of the complexity of infrastructure is being foisted onto the users themselves, as opposed to the cloud handling it for you, so you can just focus on making your beer taste better. All that stuff. None of it was fulfilled in the iCloud context. And you need to really fundamentally rethink the way cloud works, re-envisage a lot of these systems, the business models, etc., in order to fulfill the original promise of the cloud in the AI cloud context. And so I think it was clear to us that we were not on the path of that happening, that things were not moving with the right velocity, either in the right direction or with the right speed overall across these multiple angles. And so it's like, okay, we need to push this. Otherwise, we're going to definitely reach some limitations at the research level. And so we started pushing on that. And I think I was fortunate to have both a systems perspective, and at least enough understanding of, the cloud and how scheduling works and all these types of things, but then also the algorithms to see, where there are gaps where people on one side or the other weren't thinking about how you need to design the full system. We've got a lot of work to do at Foundry to, fully realize our vision, but I think we made a lot of progress so far, helped a lot of companies. We've been able to, for certain types of workloads, cut the cost by 12 to 20x, particularly for workloads that are amenable to, running in a preemptible fashion or being checkpointed or running, in a heterogeneous way or running in a batch mode where, they can run, they just need 6 hours within the next 12 hours and they don't care which 6 hours. And so for those types of workloads, we've been able to create a lot of, you know, surplus.
Yeah, when I look at Foundry and think about it in the context of other companies that are going after similar ideas, like I think of like Modal and Fireworks. It's like where I would characterize Foundry as like really pushing innovation in like the economic interface um of inference, whereas these other companies are more like Modal is pushing like the serverless idea. Fireworks is like more traditional, like you were just going to abstract away the call and you use it in a similar way. um but there are some interesting ideas in what you're doing. Like you set the price for your workload, and you're essentially this is how much it's worth to you and like run it when you can. Like that's kind of an interesting concept. And there are a bunch of other like marketplace oriented ideas built into the way you're approaching things.
That's right. Yeah. I think one way I'd characterize that is, Jensen and others have talked about how there's a couple of different regimes that you might fall in. Like one regime is you really care about low latency, and the others you really care about high throughput, right? These are a little bit different. Let's just say in the life of a researcher, let's not even go to the a user of ML. In the life of a researcher, I have some kind of verification training and debugging workloads I'm doing throughout the day as a researcher. And in that context, if I have a 5-minute, 10-minute, 20-minute, 1-hour queuing time on the cluster, I'm very unhappy. I want it to be snappy. I don't need many nodes. I want like one node quickly, and actually these are short-lived workloads. I'm willing to pay you a lot more than the typical rate of a GPU, like to get it faster, for example. In the other case, maybe I have a workload that I set off at 8 p.m., as a typical researcher, and I come back the next morning at 10 a.m. and I want it done. In that 14-hour span, I don't really care when you finish the workload. It's a 6-hour workload, finish it whenever. However, maybe as a one caveat, maybe I want it to start quickly so I can start to see the curve going down. It is confirmed, that there's no error. But then at that point, like as soon as I see the curve starting, I'm going to close my laptop and walk away, right?
And I just want it done by the time I get back.
I just want it done by the time I come back. And if you tell me that you could do that 10 times cheaper, right? Then if I need it done, just in one shot, I'm like, yeah, sure. That's totally great. If other people can do their work and there's 10 times more effective capacity on the cluster because of that, that sounds awesome. Yeah, why not, right? Versus, and then for that thing during the day, if because you're being efficient and making some things run batch, I can get my stuff snappily, even if it's a little bit more expensive, than the kind of batch rate, I'm fine with that, right? And so I think that there's this heterogeneity. Same thing with these agentic cases. There are going to be things like operator, where I want it to be really fast. Like it's way too slow. I want it to be as quick as possible, go and perform a task in real time, et cetera. And I have other things that I'll launch async that can run in the background, you know, like deep research or like the kind of async coding updates, et cetera, as long as it's high fidelity, right? And so there's these different modes. And sometimes, just like in the search case with Google, you actually have some workloads like MapReduce and indexing that are background things that you're doing explicitly for the purpose of making it fast when you need to serve. So you can have a distilled model or a really fast model or just a retriever, actually at inference time because you did all this work up front, pre-computing things, right? And so there are these different regimes, and I think you need an infrastructure, you need a cloud that can handle these regimes efficiently, pack them all. It's kind of like playing Tetris, right? It'd be much easier to play Tetris. It'd be a crazy cheat code if you could delete blocks that were kind of in a weird shape and making things hard and having them come back later. If you could take a block and split it into subblocks or make a block into sand when you need to, right? If you could make a block that's falling fall slower or just like pause it while it's falling, because it's inconvenient. If you could do these things, obviously, that'd be a massive cheat code in Tetris and will allow you to pack the space more effectively. I think something similar in the kind of the cloud context. And we want to have an economic model that would allow people to say, hey, if your workload could be deleted and come back later, then there's a massive economic benefit we can give you for that. That is, based on the effect that you're having on the overall system. I think that's kind of what we want to be able to express at the infrastructure level, which obviously requires a ton of things. There's some very heavy, virtualization and networking and, scheduling elements to this, but then also UX, business model, et cetera, elements to this. But being able to express that is like a really, really powerful thing for the ecosystem as a whole. We have this parking lot analogy I can give that I think even more intuitively and, kind of convey some of this, but I think you get the intuition overall.
As a sidebar, if someone vibe codes that Tetris game, I really want to play it. It sounds really cool.
Yeah, for any listeners out there, that is an open invitation, a challenge rather. That's right. These types of questions, like these systems utilization questions, were pretty esoteric at one point. Back when some of my collaborators or some of the senior PhD students in my lab were doing work on, using spot and reserved instances and on demand intelligently for a workload, that you were saving some cost, but these were like 20K workloads, right? And this is like the the olden days. Now, these companies are spending more on compute than on people in many, many cases, from the biggest companies like Google and Microsoft to the smallest startups to companies in the middle like OpenAI, that are, very late stage privates, et cetera. it's the primary economic budget in their P&L. And also the dollar amounts, as a result, are much, much larger. We're talking, tens of billions of dollars, hundreds of billions of dollars on infrastructure spend, and these workloads are certainly more expensive. And so these questions that were previously esoteric about compute utilization, are now central questions, right? And so, I think these are pretty fundamental to the future of the field. And so that's partly why we said, okay, we need to build this the right way.
You do this via kind of a translation layer on top of another cloud.
Phenomenal question. So we do both, right? So we have some infrastructure that we own and operate, but relatively small. But then, we can also partner with other clouds. We have a partnership we're going to be announcing relatively soon, with one of our partners that kind of shows how we do this. And we'll talk about, the way in which we're partnering to basically, it's a win-win thing. The parking lot analogy makes this clear, but if we can basically pack more work, we're creating surplus. We're creating more revenue for the owner of the compute. We can cut costs for the person whose job is being packed in there more efficiently. And then we can also, in that surplus, we can also capture upside. So it's a really nice structure. And so we want our layer to be run across as much compute as possible, ideally on every unit of compute, every single GPU, but then also literally anything that can do useful computation at a scale, sufficient scale over time. And then different workloads need security or contiguity to different degrees. And that's all managed by the scheduler. And that's partly why this layer needs to be smart. The kind of orchestration and scheduling layer needs to be smart. But yeah, exactly right. And so obviously owning our own compute, but there's a limit to how much we can scale that, particularly via venture. And so we ideally would run as a layer across, all compute, and partner with others to basically create more surplus in this way. And I think if we can do that, not only are we creating a lot of economic value, but I think also that will lead to, just the ML space being so much more dynamic, so much richer as well.
Well, Jared, this has been a great convo. I really appreciate you taking the time to talk through all the many things that you're working on. Very cool stuff.
Yeah, thank you, Sam. Yeah, really fun conversation, and really, really fun to your mind. You're pretty creative and generative, so that was a fun conversation.
Awesome. Thanks so much.